So now we want to discuss the remainder we just mentioned, which is called the Lagrange remainder theorem. Before we state the theorem, we want to look at a lemma we have already know. This lemma is actually the consequence of the Cauchy mean value theorem. You can check your notes. Suppose f has n plus 1 derivatives on I, on the open interval I. And we also suppose the case derivative of f at x0 equals 0, where this x0 is in the interval I, and k is greater than or equal to 0 and less than or equal to n. For any value x not equal to x0 in I, there exists a point C such that the C should be strictly between x and x0. Then f of x is equal to the nth derivative of f at C over n plus 1's derivative, n plus 1 factorial times x minus x0 to the n plus 1's power. Okay, so we want to use this lemma to prove the following theorem, which is the Lagrange remainder theorem. So we have the same assumption, okay, and the result is the same assumption. So f has n plus 1's derivative, and there exists a point C strictly between x and x0, such that f of x can always be written as this is the nth Taylor polynomial and plus this term. This term is called the remainder, right? So this is how we define the remainder, which is f minus the nth Taylor polynomial. So it can be, and here this theorem tells you what is the remainder is, which is given by this form. The n plus 1's derivative of f at C over n plus 1 factorial times x minus x0 to the power n plus 1. So now let's look at the proof. So we let P sub n be the nth Taylor polynomial, which is given by k from 0 to n f the k's derivative at x0 over k factorial times x minus x0 to the power k. And this is the nth Taylor polynomial for the function f at x0. And from this proposition we already have, it says this P sub n and f have contact of order n at x0. If we let Rx, which is f minus P sub n, then since P sub n and f have contact order n, so the derivatives up to the order n are the same at x0. So in other words, so Rx0, which is 0, right? R prime x0, is also 0. Then you continue. The nth derivative of r is also 0 because this is the difference. They are the same, right? The nth derivative at x0 are the same, so the difference is 0. Then we can use the lemma. We apply this lemma. Apply the lemma to this function r. Okay, so for x is not equal to x0, which is in the interval I, there exists c, right? A number c, which is strictly between x and x0, such that r x must be equal to the n plus 1's derivative of r at c over n plus 1's derivative. So the n plus 1's derivative always exists, right? Because f has the n plus 1's derivative and p is a polynomial, so the n plus 1's derivative always exists, times x minus x0 to the power n plus 1. So now let's look at this n plus 1's derivative at c, which is equal to the n plus 1's derivative of f at c minus the nth derivative of p sub n plus 1's derivative of p sub n at c. But p sub n is a polynomial at degree at most n, so n plus 1's derivative would be 0, right? So it's equal to n plus 1's derivative of f at c. So if we plug in back to here, so r is equal to f, the n plus 1's derivative of f at c over n plus 1's derivative, n plus 1 factorial times x minus a. Then we plug in this rx back to the definition, back to here. Then you will have f is equal to the p sub n plus this the nth derivative of f at c over n plus 1 factorial x minus x naught to the power n plus 1, which is the result of this Lagrange remainder theorem. So now let's look at the corollary for this Lagrange remainder theorem, which says suppose p is a polynomial of degree at most n. Let x0 be any point, because the polynomial defined anywhere, so x0 to be any point. Then the nth Taylor polynomial of p at x0 is p itself. Okay, so we have no other choice for the nth Taylor polynomial for a polynomial. It would be itself. So now let's look at a quick proof for this result. Proof. So let's fix x, which is not equal to x0. Okay. Then we use the Lagrange remainder theorem. We have there exists a c strictly between x and x0, such that p of x, this original function p minus the nth derivative of p, the nth Taylor polynomial of this function p, is equal to This is the p, the n plus 1's derivative at c over n plus 1 factorial times x minus x naught to the n plus 1. So since this p has the degree at most n, so we have the n plus 1's derivative of p at c must be 0. Therefore, we have this p sub n is equal to p, right? So this is the end of the proof.